Welcome to this problem walkthrough. In this session, we'll dive into the problem titled Swap for Longest Repeated Character Substring. We'll explore its requirements, the approaches to solve it, and key insights to help you understand the solution. Let's get started. In this problem, we are tasked with finding the length of the longest substring of repeated characters that can be achieved by performing at most one swap between any two characters in the given string. The input to the problem is a string text composed of lowercase English letters, and the output is an integer representing the maximum achievable length of such a substring. For instance, consider the example where the input string is ababa. By swapping two characters, we want to maximize the length of a substring with identical characters. The result, in this case, is 3. To understand this better, let's examine the first example. Given the input ababa, we can swap the second b with the adjacent a, transforming the string into aba. In this new string, the longest repeated substring is AAA, which has a length of 3. In another example, where the input is aabea, we can swap the first b with the adjacent a, resulting in the string aaaa. Here, the entire string becomes a single repeated substring of length 6, making it the maximum. These examples illustrate how swapping strategically can help achieve the longest possible repeated substring. Now, let's consider a different scenario where the input string is ABCDEF. In this case, each character is unique, meaning no swap can create a substring with repeated characters. As a result, the maximum length of a repeated substring is simply 1. Along with these examples, it's important to note the constraints of the problem. The string length can range from 1 to 10,000 characters, and it is guaranteed to only contain lowercase English letters. These constraints ensure that the input is well defined and doesn't include any unexpected characters or cases. Finally, let's discuss some edge cases. If the string has only one character, such as a, the output is 1 because no swaps are possible. Similarly, if all characters in the string are unique, like ABCDEF, the output is also 1, as no repeated substrings can be formed. On the other hand, if the string is already composed of the same repeated character, such as AAA, the output is simply the length of the string, since no swap is needed. In cases where multiple valid swaps lead to the same maximum length, the result should still reflect the highest achievable length. These edge cases help clarify how to handle different scenarios that might arise while solving the problem. To start, let's consider a naive, brute force approach to solve this problem. The idea here is straightforward. We evaluate all possible strings generated by swapping any two characters in the input. For each swapped string, we calculate the length of its longest repeated character substring and track the maximum length among all possible swaps. This involves iterating through every pair of indices in the string, swapping the characters, and then traversing the modified string to find the repeated character substring. While this approach is simple to implement, it's computationally expensive. The swapping process alone involves n² iterations, and for each resulting string, finding the repeated substring adds another n complexity. This means the overall time complexity is n³, which becomes infeasible for large input sizes. As such, this approach is more of a theoretical baseline rather than a practical solution for larger strings. Now, let's move to a more efficient and optimized approach that uses a sliding window technique combined with frequency tracking. The key insight here is to focus on contiguous groups of the same character and use a frequency dictionary to decide where a swap would be most effective. First, we pre-compute groups in the string, where each group contains a character, its starting index, and its length. For instance, if the input is aaba, the groups would be A0, 3, B3, 2, and A5, 1. Then, we create a frequency dictionary to store the total occurrences of each character in the string. With this setup, we evaluate three main cases for each group: its current length without swaps, its extended length if we use a swap to bring in the same character from elsewhere, and its merged length if two adjacent groups can be unified by swapping the character in between them. This strategic evaluation allows us to pinpoint the most effective swap scenarios using only linear operations. A key realization here is that we don't need to consider every possible swap. Instead, we focus on groups and their boundaries, leveraging the frequency dictionary for quick lookups in constant time. When we analyze the computational efficiency of this optimized approach, it becomes clear why it's a significant improvement. pre-computing the groups requires a single pass through the string, which is O, n. Similarly, iterating through the groups and evaluating potential substring lengths also takes linear time. This means the overall time complexity is O, n, which is drastically better than the O, n cubed complexity of the brute force method. For space complexity, we only need to store the frequency dictionary and the groups, both of which require O, n, space. This makes the optimized approach not just faster but also memory efficient, ensuring scalability for large input strings. The optimized approach using sliding windows and frequency tracking is the chosen strategy for this problem, and for good reason. It brings the time complexity down from O, n cubed, to O, n, making it feasible for large inputs. Additionally, the method is structured and focuses only on analyzing groups and their boundaries, rather than exhaustively evaluating every possible swap. This directly aligns with the problem's constraints, as we are limited to at most one swap. However, it's worth noting that this approach does come with some trade-offs. While it's efficient, it requires careful implementation to correctly handle edge cases, such as strings that consist of only one unique character or very short strings. On the other hand, the brute force method, although slower, is easier to implement for smaller inputs and may help in understanding the problem. Overall, the optimized approach strikes the right balance between efficiency and clarity, leveraging groups and a frequency dictionary to achieve linear time complexity without compromising correctness. In this problem, we're tasked with finding the maximum length of the longest repeated character substring we can achieve after making a single swap of any two characters in the string. To clarify, a repeated character substring is simply a section of the string where the same character appears consecutively. For instance, in the string AABA, AAA is a repeated substring with a length of 3. The challenge lies in determining if swapping two characters can extend that length further. To start, we can explore a brute force approach, where we evaluate all possible swaps in the string and calculate the length of the longest repeated substring for each case. This gives us a baseline understanding of the problem and ensures correctness, though it may not be the most efficient solution. Let's break this approach down step by step. The first step in solving this problem is initialization. We begin by storing the length of the input string as a variable, n. If the string's length is less than 2, we can immediately return the string's length, as no swaps are possible. Next, we need a helper function to calculate the length of the longest repeated character substring in a given string. This function, which we'll call longest_repeated_length, works by scanning the string character by character. Along the way, we track the length of the current repeated sequence using a variable like current_length, and we maintain a max_length to store the longest sequence we've encountered so far. If the current character matches the one before it, we increment current_length. If not, we update the max_length and reset current_length. Once the traversal is complete, we return the largest value recorded for max_length. This function is critical for evaluating the impact of potential swaps. Now that we have a way to measure repeated substring lengths, the next step is to generate all possible swaps. Using two nested loops, we iterate through every possible pair of indices, I, j, in the string. For each pair, we swap the characters at those indices and use the helper function longest_repeated_length to calculate the maximum repeated substring length after the swap. We then compare this result with our global maximum length and update it if the new value is larger. Once the calculation is done, we undo the swap to restore the original string, ensuring that subsequent swaps start from the unaltered input. Finally, after evaluating all possible swaps, we return the global maximum length as our result. While this brute force approach ensures we consider every possibility, it has a time complexity of O, n cubed. This arises because generating all swaps takes O, n squared, and for each swap, calculating the repeated substring length requires an additional O, n. Despite being computationally expensive, this approach guarantees correctness by examining all potential scenarios. To implement this solution, the data structures we use are straightforward. We traverse the string with simple loops, which keeps our memory usage minimal. Temporary variables help store intermediate results, such as the modified string after each swap and the lengths of repeated substrings. However, given the high computational cost of the brute force approach, there are opportunities to optimize. One key insight is that not all O, n squared, swaps need to be evaluated. Instead, we can focus on characters that are adjacent to repeated substrings or those that have the potential to extend an existing sequence. By pre-processing the string to identify and group repeated substrings, we can significantly reduce the number of swaps we need to consider. This targeted approach allows us to narrow down the problem space, improving efficiency while still finding the optimal solution. Here, we start by importing the counter class from the collections module, which will help us count the frequency of characters in the string. Inside the solution class, we define the method maxRepopt1, which takes the input string text. The first step is to use counter to calculate the frequency of each character in the string, storing this in the variable char_count. Next, we initialize max_length to 0, which will keep track of the longest repeated substring we can achieve, and end to the length of the input string. The main part of the logic begins with a while loop that iterates through the string. At each step, we determine the current character at position I and calculate the length of its contiguous block. This is done by using a nested while loop that increments j as long as the characters are the same. The difference between j and I gives us the block_length, representing the size of the current contiguous segment. We then calculate the maximum possible length of a repeated substring by considering the possibility of swapping one character from outside the block. This is achieved by checking if the total count of the current character, given by char_count, current_char, is greater than the block length. If so, we can extend the block by 1, otherwise, the length remains the same. This value is compared with the current max_length, and the maximum is stored. Finally, we prepare to handle split blocks, such as those separated by a single different character, by ensuring j has not reached the end of the string and moving forward to check for such cases. Here, we continue by handling the case of split blocks, aiming to account for situations where one character separates two segments of the same character, like a_ba. To do this, we initialize k to j plus 1 and use another while loop to find the next contiguous segment of the same character beyond the split. This loop increments k until the character at k no longer matches current_char. Now, we check if the gap between the two blocks contains exactly one different character. This is validated by the condition k j1 equals 1. If this condition holds true, it means we have a split block, and we calculate its potential maximum length as block_length plus k j, which combines the lengths of the two segments and includes the single different character. This value is then compared with max_length, and the maximum is updated accordingly. Finally, we move the pointer I to j, effectively skipping over the current block, and continue the process for the next segment of the string. Once the loop completes, we return max_length, which holds the length of the longest repeated character substring achievable with at most one swap. Here, we start by importing necessary utilities and defining the solution class with the method maxRepopt1. The first step inside the method is to count the frequency of each character in the input string using a hash map. This allows us to track how many times each character occurs throughout the text, which will be essential later when evaluating possible swaps. Next, we initialize a variable maxLength to keep track of the longest substring length we can achieve, and n to store the length of the input string. We also have a variable I to iterate through the string. The while loop begins our iteration, where we evaluate each block of consecutive repeated characters. Inside the loop, we identify the character at the current position, then use another variable, j, to find the extent of this block by checking how far the current character repeats consecutively. The difference between j and I gives us the length of this block. Once we know the block length, we calculate the potential maximum length by considering whether we can swap one additional occurrence of this character from elsewhere in the string. This is done by checking if the total count of the character exceeds the block length, allowing us to add one more to the block. The maxLength variable is updated accordingly. Now, we handle cases where the block of repeated characters might be split by a single different character, such as an a_ba. To do this, we check if there's another block of the same character following the current block, separated by exactly one character. If such a split block exists, we calculate its length by adding the lengths of the two blocks plus the one character in the middle. We then compare this split block length to the current maxLength and update maxLength if the split block is longer. After evaluating both the contiguous and split block scenarios, we move the I pointer to the end of the current block, allowing us to proceed to the next block in the string. Finally, after processing all blocks, we return the max length, which represents the length of the longest possible repeated substring after one optimal swap. To solve the problem, we start with an example where the input text is ababa. First, we calculate the frequency of each character in the string using the counter class. This gives us a dictionary, a 3, b, 2, meaning there are 3 occurrences of a and 2 of b. Next, we initialize our variables. The max_length variable keeps track of the longest substring length we've found so far, starting at 0. The length of the string is stored in n, which is 5 in this case, and we initialize a pointer I at 0 to traverse the string. Now, we begin identifying blocks of repeated characters. At I equals 0, the current character is a. We increment a second pointer, j, until we find the end of the block of a. In this case, j stops at 1 because text, j, is no longer a. This gives us a block length of ji, which equals 1. Next, we calculate the extended length of this block. Since the total count of it in the string, char_count, is greater than the block length, we can potentially swap one from another part of the string to extend the block. Using this logic, we update max_length to the maximum of its current value and block_length plus 1, which gives us 2. Then, we check for split blocks. For instance, if there's a structure like A_BA, we can combine the blocks on either side of the B by swapping in a. Here, at j equals 2, we find text, j equals b and text, k equals a at k equals 4. This creates a split block with a combined length of 1 plus 1 plus 1 equals 3. We update max_length to 3 as it's greater than the previous value. Finally, we move to the next block by updating I to the start of the next character, which is 1, and repeat similar steps for the other characters. By the end of the process, the longest repeated substring we can achieve is 3. Now, let's take a look at another example where the input text is aba. First, we count the character frequencies, resulting in a 4, b, 2. Then, we initialize the same variables as before. Max_length starts at 0, n is 6, and I is 0. The first block we encounter is for the character a. Here, j increments until the end of the block, stopping at 3, giving us a block length of 3. Since we can extend this block by swapping one additional a, we calculate max_length as max, 0, 3 plus 1, which updates it to 4. We then check for split blocks like A_BA. At j equals 4, we find text, k equals a at k equals 5. This creates a split block with a length of 3 plus 1, which is still 4. Since max_length remains 4, we proceed to analyze the next block. In the next block, the current character is b, and its block length is 2. We calculate the extendable length for this block. Adding 1 to the block length gives us a potential length of 2 plus 1 equals 3. However, since max_length is already 4, it remains unchanged. At this point, we have processed all the blocks in this string, and the final value of max_length for this example is 4. Now, let's examine a simpler case where the input text is AAAA. Here, we start by counting the character frequencies, which results in a 5. As usual, we initialize max_length to 0, and the length of the string kin is 5. The pointer I is again set to 0. In this example, the entire string consists of a single block of the character a. The pointer j increments until it reaches the end of the string, giving us a block length of 5. Since the string is already a single block and there are no other characters to consider, the extendable length remains 5. We calculate max_length as the maximum of its current value and block_length, which updates it to 5. This means the longest repeated substring for this input is simply the full string itself. The final result for this example is max_length equals 5. To analyze the time complexity of our solution, we begin by breaking down its key operations. First, the counter function computes the frequency of each character in the string text. This requires a single pass through the string, making it an O(n) operation, where n is the length of the string. Next, the outer loop iterates over the string to identify blocks of contiguous characters. Since the pointer I skips to the end of each block after processing, every character is part of exactly one iteration, leading to O(n) time for this loop as well. Within the outer loop, an inner loop determines the length of each contiguous block of characters. Again, since each character is processed only once, the total contribution of all inner loops is O(n). These operations demonstrate that the primary loops of this solution collectively run in linear time, O(n). Now, let's consider the handling of split blocks, where the algorithm checks for a second block of the same character after skipping one character. Here, another loop is used to measure the length of this second block. Like the previous loops, this step also processes each character at most once, contributing O(n) time. Combining all loops, we see that the total time complexity remains O(n). Finally, additional computations, such as comparisons and updates to the max value, are performed in constant time, O(1) per iteration. This confirms that the overall time complexity of the solution is O(n). Shifting focus to space complexity, the counter object used to store character frequencies requires space proportional to the number of unique characters in the string. If U represents the number of unique characters, the space complexity of this step is OU. The total space complexity of the solution is primarily determined by the counter object, which needs OU space to store the character frequencies. For strings containing only lowercase English letters, the maximum number of unique characters is 26, so the space complexity simplifies to O(1) in practical scenarios. However, for strings with arbitrary character sets, the space complexity remains OU. Let's compare this solution to a brute force approach. A naive method would involve generating all possible substrings of the input string and then checking the length of the longest repeated character substring after performing one swap. Generating all substrings requires O(n) superscript 2 time, and validating each substring adds additional computation, resulting in an overall complexity of O(n) superscript 3. In contrast, our optimized solution processes contiguous blocks of characters directly and uses the counter to efficiently determine character frequencies. This reduces the time complexity to O(n), a major improvement over the brute force method. Examining the best, average, and worst-case scenarios, we find that the time complexity remains O(n) across all cases due to the linear nature of the algorithm. In the best case, if the string consists entirely of one repeated character, like AAA, the outer loop processes the string in a single iteration with minimal additional work. While the complexity is still O(n), the constant factors involved are smaller. For typical input strings with a mix of characters, the algorithm processes each character once in the outer and inner loops, maintaining O(n) complexity. In the worst case, such as a string alternating between two characters, like abababab, the algorithm encounters many small blocks. Despite this, each character is still processed exactly once, so the overall complexity remains O(n). To summarize, the time complexity of the solution is O(n), and the space complexity is OU, where U is the number of unique characters in the string. For strings containing only lowercase English letters, this space complexity simplifies to O(1). The optimized solution stands out as significantly more efficient than the brute force approach, especially for larger strings, due to its linear time complexity. By directly processing contiguous blocks and leveraging the counter for character frequency calculations, the solution achieves a balance of simplicity and efficiency. When tackling this problem, there are several common mistakes to avoid. One frequent misunderstanding is assuming that swaps must only occur between adjacent characters. This can lead to overly constrained logic, so it's important to clarify if any two characters can be swapped. Another pitfall is overlooking edge cases. For example, how does your solution handle empty strings, single character strings, or strings where all characters are identical, like AAA? These scenarios can behave differently from more general cases. Additionally, brute force approaches might seem tempting but are often impractical for larger inputs due to poor time complexity. For instance, generating all possible swaps explicitly in O(n) superscript 2, or even O(n), can quickly become computationally infeasible. Finally, don't forget to validate your input. If the problem allows non-alphabetic characters or unexpected symbols, failing to account for these can lead to runtime errors. Similarly, mishandling duplicate characters can result in redundant computations or incorrect results. Each of these mistakes can derail an otherwise promising solution, so addressing them early is critical. To perform well in interviews, it's important to keep a few key insights in mind. First, if you start with a brute force approach, quickly identify patterns that allow you to optimize. For example, techniques like using hash maps or frequency arrays can help reduce redundant calculations. It's also vital to clarify constraints with your interviewer. Ask whether swaps are limited to adjacent characters or if any pair can be swapped, and inquire about the maximum expected input size. This ensures your solution is both correct and efficient. Recognizing common patterns in string manipulation problems can also give you an edge. Techniques like two-pointer methods, sorting, or leveraging frequency counts often apply across multiple problems. Demonstrating awareness of edge cases such as empty strings, single characters, or strings with duplicates not only shows thoroughness but also helps build a robust solution. Lastly, always discuss time complexity trade-offs. For example, if you choose a more readable approach like O, n log n, sorting over a highly optimized solution, explain why it makes sense given the problem's constraints. This problem shares similarities with several other LeetCode challenges, which can help you build transferable skills. For instance, LeetCode 567, Permutation in String, involves checking whether a permutation of one string exists as a substring in another. This problem encourages you to think about sliding windows and frequency counts, which are also useful here. LeetCode 49, Group Anagrams, focuses on grouping strings that are anagrams of each other, often using sorting or hash maps. Another related problem is LeetCode 31, Next Permutation, which teaches you to rearrange a sequence into its next lexicographical order, a skill that can be useful in understanding permutations and swaps. Finally, LeetCode 5, Longest Palindromic Substring, challenges you to identify palindromic patterns, which requires attention to sequence structure and optimization. Studying these problems can deepen your understanding of string manipulation and help you recognize recurring techniques. There are also several alternative approaches to solving string manipulation problems, each with its own trade-offs. A straightforward method is sorting. For example, if you're determining whether two strings are permutations of each other, sorting both and comparing them is simple to implement, though it has a time complexity of O, n log n. For a more efficient alternative, you can use frequency counts with hash maps. This approach runs in O, n, time and is particularly space efficient when the character set is limited, such as lowercase English letters. Another common technique is the two-pointer method, which can streamline problems involving swaps or rearrangements by reducing unnecessary computations. When combined with sorting, it becomes even more powerful. Finally, for generating all permutations or swaps explicitly, backtracking or depth-first search can be used. However, these methods have factorial time complexity, O, n, and should generally be avoided unless the problem explicitly requires generating all possibilities. Each of these strategies has its place, depending on the constraints and goals of the problem. Great job following through this problem. We've covered the core approaches to solving swap for longest repeated character substring, and you now have a solid understanding of the concepts involved. Don't forget to practice similar problems to reinforce your learning. Thank you for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!